Hey guys, today we're going to talk about a new type of equation that we're going to start working with, and that's called polar. So your essential question is, how do I convert points into polar form? So the type of points and systems we've been used to working with are the rectangular coordinates. And so rectangular coordinates, the normal ones, Cartesian, all the ones that you've learned since whenever, are in the form x comma y, where you have your xy axis and you go side to side or up and down depending on if you're negative or positive. Now polar coordinates are going to be in the form r comma theta. And r is going to represent a radius and theta is going to represent an angle. And so the weird thing about these guys is we're used to always going left or right and then up or down. But with polar form, you actually want to know what angle you're going to first, and then you graph your radius after that. So if I wanted to graph something in polar form, we're going to start at the center, and the center is going to be called your pole. So the center of my axis is called my pole. It's polar form. So it's just like when we graphed an angle on the unit circle. So I'm going to start on that horizontal line. Here's my pole, and then I'm going to go to an angle. So for instance, maybe I want to graph the point 3 comma 45 degrees. So remember, this is a radius and this is an angle. So the first thing I'm going to do is go find my 45 degrees. Well, this would be about 45 degrees. And then the weird part about this is we're going to go ahead and make a radius on this ray. So I'm going to say if this was 1, 2, and then 3, this is where my point would lie. So I go to my angle line and then I go graph my radius. And that's all that polar really is. So if you look at the note skeleton that I hopefully handed out to you yesterday, we're going to look at this guy, and this is polar graph paper. So we're used to seeing our regular grid paper, but this one's polar graph paper, and so you see it's got all of the angles marked on it just like our unit circle, but it also has little radiuses inside. So that's how we're going to count out my little tick marks on my lines. So for the first example, it says graph the following polar coordinates. And again, like I said, it's kind of easier to go find your angle first and then go graph your radius on it. So if I try to graph 5 pi over 3 and I didn't have any of my lines, remember that this guy would be 6 pi over 3 because it's 2 pi. And so I'd be either going down or I want to go almost all the way around my circle. So here's 5 pi over 3, and I'm going to go ahead and I'm going to put a line on it just so we can see it. Well, that was the biggest line in the history of the world. Let's make it a little thinner. Okay, and so there's my 5 pi over 3 angle. Then what I'm going to do is I'm going to count that radius out. So my radius is 4. So I'm going to go out 1, 2, 3, 4 tick marks, and that would be my point P. Okay, so then if I wanted to graph something like Q, again, pretty straightforward. All I've got to do is go find 7 pi over 6, which is right here, and then I go out 3. So this is my 7 pi over 6 angle, and then I'm going to do 1, 2, 3, and this would be my point Q. Okay, now, things get a little bit more tricky when we get things like a negative radius. And so with a negative radius, all that's going to mean is that we're going to go backwards. So I'm going to make a note of this. Okay, so when I go find my angle, I'm going to go find 5 pi over 4. And if you notice, it's not actually marked in here. But I do know that the angle in between pi over 6 and pi over 3 would be pi over 4. So if I look in between this one, that would be 3 pi over 4. And this is 4 pi over 4, so this guy must be 5 pi over 4. So this is the angle that I care about. And so normally on my 5 pi over 4 angle, and let me go ahead and get a line in here so that way I can actually see it. Make it yellow. And normally on here, I would just go ahead and say graph 2, and then I'd be done. But since it's negative 2, all that means is that I'm actually going to take this line and I'm going to go backwards. And so that was my 5 pi over 4 line, but since it was negative, I'm going to go backwards up here, and that's going to be my point R, backwards 2. So the interesting thing about polar is there are infinite ways that I can write this particular point, because I could have also written it with a positive radius and just said it was pi over 4 was my angle. So I would have 2 and then positive pi over 4. Okay, so a lot of times you'll see these written in a lot of different ways. Now when you have a negative angle, it's a little bit less confusing because that just means instead of going counterclockwise around, you go clockwise around. And so if I had negative pi over 3, that's the same thing as 5 pi over 3 if I was going backwards, and it's only got a radius of 1. So this guy right here would be my point S. So that's how you graph a polar coordinate using our little polar coordinate thing. Now the big thing we want to know is how do these relate to the forms that we're already used to? And what we're going to do is we're going to go back and think about this picture that has been drawn a lot for you. So we have a triangle. We're going to call this angle theta, the one that's formed with the x-axis. And then I know if I knew what this point was, we called it xy. So I went over, I don't know what the cats are doing. I'm going to go over x and up y. And then I know that since this is going to form a triangle, and we're going to call this r, because it's like the radius of my unit circle. So if I was to use my trig SOHCAHTOA values, I would know that cosine of theta would be my adjacent over my hypotenuse. In this case, my adjacent is r, x, and my hypotenuse is r. Okay, so if I wanted to convert this and make this into x equals, I could just multiply both sides by r and find that x is equal to r times the cosine of theta. Okay, similarly, I can do the same thing with sine, except for that's going to be opposite over hypotenuse. And again, multiply both sides by r sine theta. It's supposed to be sine. So if you recognize this, this looks a lot like our vectors that we did a couple weeks ago. And this right here, these two formulas, are what we are going to use to convert from polar coordinates to rectangular. So if you already know your polar coordinate and you want to make it into an xy form, this is the formula you're going to use. Now, if we continued on and finished filling out my chart, tangent of theta is again going to be your opposite over your adjacent. So I'd have y over x. So that would be that last ratio here. We also know that with the Pythagorean theorem, if I took x squared plus y squared, since this is a right angle, that my hypotenuse squared would get me this guy, Pythagorean theorem. So if I wanted to solve this for r, I could square root both sides and know that the square root of x squared plus y squared is going to be r, which is very similar to the magnitude of a vector. Okay, so again, we're going to take these guys, these 3/2 formulas, since two of them are the same thing, and this is going to be how we convert from rectangular to polar. So if you're given an xy, how to make it into an r theta. Okay, so let's go ahead and practice doing this. We want to convert 4 pi over 6 to rectangular coordinates. And again, we're going to use those two formulas that we just talked about. So this right here is my r, and this is my theta. We have my angle, we have my radius. So I know if I want to find the x coordinate, I go ahead and x matches with cosine, because we talked about that, you know, even with our unit circle back in the day. So I'm going to take my radius times the cosine of 5 pi over 6. So here's why you have to remember your exact values, because otherwise how are you going to figure out what that number is? So I'm going to go ahead, I can just draw out my 5 pi over 6 angle. 5 pi over 6 is going to be before pi. Wow, that was a terribly drawn one. And then we know pi over 6 was going to have a reference angle of 30 degrees. So opposite that guy is going to be 1. My hypotenuse is 2, and be careful, since this is in quadrant 2, this will be negative root 3. So if I wanted to find the cosine of this, I would take my adjacent over my hypotenuse, and I'm multiplying it by the radius, so all I have to do is take out a 2 there, and I would get negative 2 root 3. Okay, I'm going to do the same thing for my y coordinate. I'm going to take my radius and times it, though, by the sine of the angle that they gave me. So my picture still stands, which is nice. I only had to draw it once. And I'm going to have my opposite now over my hypotenuse, and 4 times a half is just 2. So into rectangular coordinates, into an x comma y that I'd be used to graphing, would be negative 2 root 3 comma 2. So again, that's very similar to the vector operations that we were doing a couple weeks ago. Just remember, x goes with cosine, y goes with sine. So what about if we wanted to go backwards and we wanted to take something I knew in rectangular form and go ahead and put it into polar? Now the first thing I'm going to tell you here is you need to graph these. You need to draw them, because it could be easier than you first expect by looking at these things. So if I go ahead and I draw this guy, I'm going to go right pi over 3, root 3, and then I'm going to go down 1. And so this is this point that I'm looking at right here in rectangular. But I want to write this in polar. I want to write it in r over theta. So when I write this thing down, I can use those formulas that I have. And the first one is that my tangent of theta is equal to my y over my x. And so in this case, my y was -1 and my x was √3. So in order to find that angle, all I'm trying to do here is find the inverse tangent, find the inverse value of -1 over √3. Now you have to be careful, especially if you try to type this into your calculator, because your calculator is going to give you the principal inverse value. So you need to watch where your thing actually got graphed. But I do know that this guy is going to match with this picture, and if I'm thinking about this and I tried to make this into a Pythagorean thing, this would be 2, and we know that that's a special right triangle where this one is pi. Well, let me do this in degrees for a second. This one would be 30 degrees, right? The reference angle. So the only problem here is that they said, apparently mine doesn't say it, but they wanted you to do it from 0 to 2 pi. So I have to think about my constraints and how I would get that 30-degree angle, and so that would be the 11 pi over 6. So my theta for this guy is 11 pi over 6, thinking about what constraints they gave me. So the last thing I need, though, is I need my radius. And there was a formula for that. We had that r equal to the square root of x squared plus y squared. And so I could plug all those in, and my x would be √3 squared, and my y would be -1 squared, and I would solve that, and I would find that it's actually this ratio right here, and you should get that it was 2. Okay, and so when I write my point, I write it r comma theta, so 2 comma 11 pi over 6. Okay, and remember, we were just following that range, that 0 to 2 pi. You could have written this using, there we go. You could have written this using different theta values, but I just wrote it in between that thing. Okay, so here's the point where you really want to make sure that you're actually graphing this, because this guy is going to be a lot easier than you first thought. So if I look at this one and I plot these points in just rectangular form, I go 0 over and I go -2 down. So if I wanted to name this point, this is on an axis, and if it's on an axis, that means that it's one of those special quadrant angles. And so if I had to go all the way around, I would know that that angle would be 3 pi over 2, or 270 degrees. And then I think about my radius, how far away from the pole or the center is it? Well, it's just 2. So that means if I wrote my point, I would just write my radius, comma, the angle. So a lot easier if you draw it first instead of trying to do all those fancy formulas. Okay, you can still do the formulas, it's just going to take you a little bit longer. The last thing we need to do is equations. And equations are pretty straightforward. The thing that you're trying to do here is get rid of any x's and y's, because we're in r theta now if I want to make it into polar form. So if I think about those formulas, and you can always have those formulas next to you when you're looking at this, I know that my x-coordinate is equivalent to r cosine theta. So I'm going to go ahead and just change my x and make it into an r cosine theta. Now my equation is in all r's or thetas, and I would be happy with this. Okay, you could also solve it for r by dividing both sides by cosine. And then you know if you have cosine in the bottom, you actually have that secant value. So you could have solved it and left it like this. Okay, so either of these answers are correct. There's no more x or y's, we're good. If I look at letter B, you're going to recognize that this one is a circle from what we did the other day. And if you look at your other formulas that we did, we know that x squared plus y squared is equal to r squared. So if I could get rid of all my x's and y's just by writing this. Now if I wanted to just make this say r equals, I would just take the square root of both sides. And because we're looking at polar, we don't have to worry about the negative part. It's kind of taken care of. So what we have here is we have something where no matter what my theta is, the radius is always 4. Which makes sense, because if I start at my pole, and I always have 1, 2, 3, 4, and I'm going all the way around 4, no matter what my angle is, I'm going to get a circle. Okay, and that's in polar and in rectangular. Okay, now the other way, going from rectangular, going from polar to rectangular, same idea here. You're trying to eliminate your r's and thetas and replace them with things you know. So r cosine theta, cosine goes with x, And r cosine theta is actually my complete expression for that. So this is just x equals to 3. And if I remember my Hoy-Vux from back in the day, Algebra 1, I know that that's going to be a vertical line at 3. And then if I have theta equals pi over 3, this one gets a little bit more tricky. But what I can do here is I know something about the tangent of theta, because tangent of theta is equal to y over x. So what I'm just going to do here is I'm going to take the tangent of both sides. Okay, so if I take the tangent of theta is equal to the tangent of pi over 3, then I can just go ahead and replace the tangent of theta, I didn't put my theta in there, with y over x. And then I know the tangent of pi over 3, well, that's just some number. So I'm going to go ahead and I'm going to figure out what that is. So pi over 3 is equivalent to 60 degrees. So this would be root 3, 1, and 2. And so my tangent is going to be my opposite over my adjacent, which is root 3 over 1. So then, if I wanted to make this look like an equation, you know, a y equals equation, I could just multiply it by x on each side, or cross multiply, and I would get y equals to the square root of 3 times x. And so all I've got here is a line that has that slope of root 3. And if you think about it, and I had my angle thing going on here, if I had theta equals to pi over 3, that's that angle 60 degrees. And again, you can go backwards because r doesn't matter in the polar form. And if I had a line, I would have to keep going in all the directions. Okay, and that's what I've got for you about polar. We're going to continue looking at these tomorrow, and eventually we're going to graph some graphs.